going through the first chapter of Engineering Studies, the Definitive Guide, Volume 1, Second Edition. This is not the current edition, but this book by Paul Copeland I think is an excellent book, and I'd recommend it to anyone. It covers effectively the first chapter of the the first term of the Year 11 course. It's broken into 4 sub-chapters. There's one for historical and social influences. The next section is on mechanics and hydraulics, which is sort of the maths. The third section is on materials. And then the fourth section is on communications, which usually the fourth section of each chapter focuses on drawing standards, but there's also a little bit of stuff on report writing and research and references and those sorts of things. Okay, so to start off with, I'm going to go through the historical and social influences. And when I teach this in class, I usually get timeline cards. So I get 100 little cards that I ask students to arrange in order. And I think I include all of these things on this list, and several dozen more. The first thing is... The first thing to talk about, and I just had as a student question, is how much do you need to know when it comes to history? The answer I'd say there is, well, okay, the scope of engineering history is unknowable. I mean, it's certainly the scope of more than a PhD, but what I would say is there are some key highlights that we should really be focusing on. There's some things that you need to know to not embarrass me. And then there's there's a level of how specific does your knowledge need to be. Now, my attitude is that your knowledge needs to be specific in terms of general ranges. So you should know that there are some things that have been used that were older than writing. So they're prehistoric. They exist before history. They were used before there was writing. We know it through archaeological evidence. The next thing we have stuff that was used by the Romans or used by ancient civilizations, so ancient history. Then you could talk about things that are in the Middle Ages. Some bridge technologies, for instance, are in that ballpark. Maybe the suspension bridge a little bit. I wouldn't say that was really... I would say that was... Moving on. The point is, the next major era that we're interested is in the Industrial Revolution. So a lot of the things that we're looking at from the steam engine on, we would be talking about as the Industrial Revolution. And then the next major points that we're interested in are World War I and World War II, and then post-World War II. So if you group things into prehistory, ancient civilizations, the Industrial Revolutions, World War I and World War II, and then the modern era post-World War II, I think that gives you a pretty good level of how accurate you need to be. Okay, so I'm going to group some things. I'm not going to read out this entire list, but I'm going to group some things into general knowledge. Okay, so into general categories is what I mean to say. So first of all, we have the wheel. So wheel is the fundamental aspect for transport. The idea that rather than having to lift objects up, and rather than having to slide objects along the ground, which both of those things are very difficult. If you want to lift objects up, you have to be able to carry effectively the full force of their weight under gravity. Sliding things, you're exposed to huge amounts of friction. The wheel overcomes those things. This is where anyone who's ever moved a fridge appreciates the value of having a dolly. A trolley, I guess, is another word for it, to carry things. Okay, so bronze is specified here as the first alloy. So there was metal casting prior to bronze, but this is like gold and pure copper. But bronze has an important part in shaping of metals in early engineering. Okay, so the arch is important as a structural feature, which is used a lot in not just buildings, but also bridges. We will talk a lot about stone arch construction, it's particularly in the beginning of the HSC course. We talk a lot about that. Then we get to iron. So iron was used along with bronze, but for instance, the ancient Greeks used iron in addition to bronze. But bronze was a lot sharper, whereas iron still had applications. The next one, we have a suspension bridge. So we have some very old suspension bridges, which we do talk about in the start of the HSC course when we talk about bridges. But effectively, it wasn't until the 18th century, so that means 17 something, when the first suspension bridges were used. Clifton developed the suspension bridge as we understand today. The idea is that many of you might be familiar with sort of rope bridges, whereas something with a solid deck was the Clifton bridge, which would move a few steps down the list here. Okay, so the steam engine is probably where most people would say the Industrial Revolution started. This is the first time that we really had access to power. I mean, people have always had access to things like wind and water power, but most of the time, most engineering power, the thing to move objects, was done by either humans or animals. So boats run on wind and some things that we can use water pumps. But steam engine really was a huge innovation beyond that. Cast iron is also really important in the commercialization of and mass-produced products. So things like cast pots, which once would have been a very, very expensive heirloom object, was now something that was much more affordable and readily available for a growing population. Then we get to steel, developed by Henry Bessemer. This is a also a very important part of the Industrial Revolution, and this allows for the structures that steel is now probably the most important engineering material, especially for its role in concrete. That it is, I'm making a special point to point out how important steel is. Okay, so then we have the internal combustion engine, the Otto cycle engine. We have aluminium. So aluminium was so expensive when it was first used that the French nobility threw out their gold, well, probably didn't throw out, but they replaced their gold cutlery with aluminium cutlery because it was that expensive and desirable. We have developments on the engine. We have the advent of AC electricity, which initially was not as widely used as we might imagine today. The main application for that was for lighting, to replace gas lights, but over time it quickly found use in a variety of applications. Most things can really be, many things in early uses of electricity could be related to either motors or compressors, but these days, obviously, electricity generally has allowed us to run computer equipment, which drives our modern economy. Okay, the human flight in 1903, I think that's a date that I think is fairly significant. That's probably, if I was only going to learn one date, that would probably be the one I'd learn. Human flight, obviously, there was always flight prior to the Orville and Wilbur Wright in terms of heavier than air. And there were a lot of people who contend that there were other examples of heavier than air flight prior to the Wright brothers. But for the sake of our argument, we're not going to go into those debates. We're not engineering historians. We are people who want to know ballpark time periods. And we know that in about 1903, heavier than air flight was developed. And I think a lot of people, they think that originally it was just sort of people riding bikes. And they did own a bike store, but very quickly they developed motor engines, and they could control flight. They could fly, even though the first flight was very short. Very quickly they were able to fly reasonable distances, sustain flight for a few minutes, and then land back where they started. Stainless steel is an important modern alloy. Helicopters are obviously an important innovation on flight, but the gas turbine engine, effectively the first jet developed. Again, there's some contention about whether or not it was the Germans or the English who developed this. The Frank Whittle and the Whittle engine is generally the one that we give that credit to. That's probably because the English won the war. But this is, when we think of modern flight is almost always with gas turbines, so we will talk about times where that's not the case. Then finally, the last two entries here really are trying to identify topics that we're going to talk about later in later chapters. So the very last chapter we do at the end of Year 12 is telecommunications, and the transistor is effectively the key to modern telecommunications. Computers don't work without transistors. They're the fundamental component of how transistors work. The next dot point is the pacemaker. The pacemaker is, I guess, what they've used as their token for biomedical engineering and innovation. There's plenty of other alternatives you could use. Everything from, on my list, I have the Roman Capua leg, which is one of the first prosthetics. I have things like artificial hearts, which get a lot of talk, get a lot of coverage in in these two textbooks. This volume 1 and volume 2 of the textbook. MRIs and X-rays, I think, are really important. Even the stethoscope is an important diagnostic tool. Things like radiotherapy as a treatment device. Things like self-driving wheelchairs and assistive devices like just typewriters that can be used by people with paralysis. But the pacemaker is the one that we have here. Okay, so the next chapter here, the next section here is just talking about why do people do engineering? Why does this matter? And in the HSC, there's a list of HSC keywords that are available on the internet. I will definitely show them at some point in class, but if I haven't, I'm going to say if I haven't shown them now, I'll look at them later. I'm not going to open a browser at the moment to look at it, but the point is that analyze is a really important verb, and the way I teach analyze is, I believe the actual text is relationships and implications, or it includes that concept of relationships between things and their implications. I like to think of it as, why do I care? Why does anyone care about engineering? Why do people want to be engineers? What do engineers do for the real world? Well, when I was at uni, I remember I had a lecturer who used to talk about how engineers were the only faculty that actually did anything. I think he maybe gave science a pass, but he said basically every other faculty, all they did was move money from one bucket to another. Now, I'm sure that if anyone here ever needs a lawyer, that you'll probably feel differently about it, and I'm sure that there's a lot of people who would argue the importance of the humanities, but nevertheless, there is definitely something to be said about engineers are what keep us dry in the storm. I often find it interesting. So my brother is a doctor. I'm sure you'll hear me mention that many times in these recordings. But doctors have a fairly high prestige in our society, and I think that's quite appropriate. My brother would disagree, but I think that's quite appropriate that they do. But the fact is that when people get a treatment for a disease, when someone has cancer or if someone has a heart transplant, they thank that doctor and they say, "Thank you, you saved my life." Whereas what no one ever considers is how plumbing to your home literally saves people's lives. Arguably, and I come from a family of plumbers, and they talk about how plumbing probably has saved more people than modern medicine has. Penicillin's pretty important, but there's definitely something to be said about the importance of running water, that not having to spend an hour of your day going and getting water, but also the elimination of diseases from the waterway, having a clean place to dispose of your bodily waste. All of these things are pretty important. An experiment that anyone can try is just try 1 or 2 days without running water. Just turn off the water at your mains and see what it's like to spend 2 days without water. And the first time that you use the bathroom after you've turned off the water, you'll really appreciate just how important running water is in your house. Another example is electricity. Electricity, let's say it costs $2 a day. I probably am way off on what your family's electricity bills are. But even at the rate of $5 a day, I would happily every day put $5 in a jar if it meant that I could have electricity. I think electricity is just an absolute bargain. It's an excellent deal. The internet is a fantastic deal, and this would not be possible without engineers. Things that we take for granted, or things that we used to take for granted before the global pandemic, of international travel, which wouldn't be possible without aviation. And a lot of the medical innovations that we take for granted really are dependent on the work of engineers. So that's my answer for the effect of engineering on people's lives. Even things like the replacement of potholes. It's not until people stop replacing potholes that you really notice that this work is happening all around you all the time, and that things like roads that work, we just really take for granted. Okay, so that's, I'm not going to read through the notes. I'm sure that that we'll go through that at some other point, or you'll read it as a for homework. The thing that's worth mentioning is there's many different kinds of engineers, and I have a series of notes that I talk specifically about the engineering disciplines. So off the top of my head, and I may end up forgetting one, I always start with civil. Civil is the oldest field of engineering, and that's what I was before I went into teaching. But then the next one chronologically is mechanical engineers. So civil engineers were originally civilian engineers. They were engineers who didn't work for the army. They were the people who built bridges and structures and roads and the things that allow civilizations to flourish. Eventually, with things like the steam engine, there was a need for specialization of engineers who knew about how engines work. And eventually, with the advent of electricity, there was a need for engineers to specialize as electrical engineers. So that's 3. Then there's chemical engineers, there's biomedical engineers, there's environmental engineers. There are also these days, there's information and technology engineers. And then beyond that, we also have some sub-disciplines, things like, where we might consider aeronautical as part, I would consider that to be part of the mechanical discipline. And we have things like mining that is also part of the mechanical discipline. We also have things like photovoltaics, so renewable energy, that's all part of electrical. And then we have things that are a combination, so mechatronics, which I think is a really interesting and important area of engineering. That is kind of a combination between mechanical and information. So the big thing that all engineers really need to work on is all engineers need to predict forces or demands on whatever it is they're designing. So in the case of a civil engineer, an engineer needs to predict what kind of forces the structures that they design are going to be exposed to. Electrical engineers, they have to predict what kind of demand for electricity there's going to be. A biomedical engineer has to consider what kind of conditions the replacement part that they're going to produce is going to be exposed to. And when you consider that, so first of all, engineers have to start with a prediction. Once they've had that prediction, the next thing that a designer will do is they'll have to come up with a solution that they feel best meets the conditions that they're asked, or that's asked of them. The way I put this is anyone could build okay, maybe not anyone, but it doesn't take an engineer to build a bridge. It takes an engineer to build the cheapest bridge that's safe and meets the needs of its community. That if you just say, hey, Jimmy, you know how to build stuff, go and build this bridge. Well, Jimmy might do that, but Jimmy might do that for twice the cost of what an engineer could do it. So it means instead of having 2 bridges, we only get 1 bridge. Or Jimmy might build a bridge, but he doesn't, because he hasn't correctly analyzed or predicted the forces and taken the requirements of the bridge into account, the bridge might not meet the needs of the community. In the case of bridges, it's pretty obvious if the needs are not met. But in other fields like, say, telecommunications, it's much less clear, immediately apparent what the needs of those things are. Also, we think about things of, it doesn't necessarily mean what is the cheapest bridge, but it's what is going to be the best bridge for everyone involved for the longest time. So when we say everyone involved, we usually use the term stakeholders, but the best bridge that's going to meet the need of stakeholders for a long time. So I like to say that engineers find solutions that meet the needs of stakeholders. Now, that's a pretty vague term, but I mean, you could argue that teachers find solutions that meet the needs of stakeholders, and doctors find solutions that meet the needs of stakeholders. But in the case of engineers, that's I think the best terminology that I can use that encompasses what all engineers do. Okay, so there's a suggested research task, and that is not a bad piece of homework to do in your first couple of weeks of the course. Okay, so the next thing we're going to do is we're going to move into, so this is a big change, we're going to a whole new section of the book, and this next section of the book, the next subchapter is mechanics. So whenever I write my notes, I usually use the symbol X for mechanics for whatever reason. It's just a habit I have now so that I can distinguish it from materials. And mechanics is where we have the mathematics component of engineering. Now, often, the first year of engineering, the year 11 course, I feel as though it doesn't reveal the level of maths until it's kind of too late. I try to bring forward a lot of the maths so that students can see, can have a good idea of what's involved. And it's fair to say that not every engineer necessarily has to do maths to be successful. As a matter of fact, I would say many engineers manage to go their working life very rarely using mathematics. But I would say it's the fundamental understanding that every engineer needs to have. Even though many engineering managers the only maths that they ever do is calculating dollars and cents, I would argue that those managers need to have a fundamental understanding of forces, of electrical engineers need to understand about currents, biomedical engineers need to understand about the needs on the human body. And although there are many engineers who can avoid maths, I would say this is a fundamental aspect of the course and pretty important. Now, the next thing is, how much maths is there in to be an engineer? Well, for me, I worked as a civil engineer for 4 years. The last thing I did before I quit was I was chartered from the Institute of Civil Engineers, or Engineers Australia as it's called in Australia. And in my daily life, I worked as a designer for some of those years, and I did not need a very high level of maths. I don't think I can ever recall using calculus as part of my professional life. There are definitely engineers who do. So water engineers, like hydraulic engineers, electrical engineers, they probably have to use calculus a lot more than I did, which just to say that I didn't use any calculus. But I did need to use, I need to have a high understanding of basic algebra. You have to be very, very comfortable with basic algebra. And as we'll find out very soon, you need to be very comfortable with geometry. You need to be able to do pretty much year 9 level trigonometry. Yeah, in the course, that's pretty fair. Year 9 level geometry, and have a really solid understanding of algebra. Now, the fact is that to become a civil engineer, you will have to do higher levels of maths. So you will have to do some pretty advanced calculus to be able to one day be an engineer. You just won't need to do that in this course. So I did high-level calculus in my first 2 years of university, but after that, I pretty much didn't use it again. So I think that's an important consideration to say that engineering often attracts people who like maths, and sometimes people are dissuaded because of the level of maths. And I just like to be upfront that in this HSC course, as long as you can understand this level of mathematics, which is to say that you can understand Pythagoras' theorem and trigonometry ratios, you will probably be okay. This next level here, where we're going to the cosine and sine rule, to be honest, I don't use those ever in my solutions, but I have some tricks that I use to get around that, and that knowing the sine rule and the cosine rule could make your life a little bit easier. What I will say is that if you're listening to this and thinking, oh my God, I know nothing about trigonometry, what I'll say is there are a lot of resources out there to help you. Things like Khan Academy and Maths Online provide really good resources for people to learn trigonometry. I will also say that in a lot of my responses, I have memorized trig ratios, and I find that knowing the trig ratios for 60-degree triangles and for 45-degree triangles is really, really important. So when I say this, I mean right-angle triangles. This is really, really important. I think that it will drastically improve your intuitive understanding of the course. Okay, so now that I've said that, I think that's my outline for mechanics as a concept. This is a big section heading, and this is, for me, I think this is probably the hardest part of the course. This is where most people spend most of their study, and this is the thing where most people have anxiety, where most people have trouble. So let's approach that. Okay, in this first chapter, I'm pleased to say that there's not a whole lot you need to worry about. What we're going to look at is we're going to look at units of measurement, which are pretty important. And then the next focus we're going to look at is we're going to get to simple machines. Now, I watch a series of videos that were made in Canada from the 80s that I think were fantastic. My mum showed them to me when I was about 8, and I just thought they were amazing then, and I still use them now. And I generally have pretty good feedback when I speak to students about it. But let's have a look at what we've got here. Okay, so first of all, they're talking about SI units. And you might say, what are SI units? Well, they have standard metric system units. SIMS, okay, that's a terminology. In my notes, I use the Système International d'Unité, but for us, we're just going to go with SI units is the acceptable term for this. Now, the idea here is that not everything that's a metric unit is an SI unit. So an example would be the cubic meter and the litre both measure the same thing. And as a matter of fact, a milliliter and a cubic centimetre are exactly the same concept. It's just that we typically use litres for fluids and we use cubic meters for everything else. The fact is we can measure liters in those units. Obviously, it's worth mentioning that not everyone uses the metric system, America being the obvious example, and their system is, we're going to use not a user-friendly system, and I think with that we can move on. Obviously, I've already recorded several notes that go into that in excruciating detail. Pretty much the only ones that we need to know in this course are the meter, the kilogram, the second, and the amp, or the ampere. We do use some others, like obviously we're going to use a whole bunch of derived units that I'll discuss in a second. I'll also mention just quietly that Kelvin is not listed there, or degrees Celsius for temperature. We do reference that very, very vaguely when we talk about metallurgy, but generally it's not relevant. So it's worth noting that Kelvin is the SI unit for temperature, not the degree centigrade. If you don't know what that is, a quick trip to Wikipedia will explain that, I think, pretty easily. If you don't understand that, simple Wikipedia. I know that might sound flippant, but the whole point is to say that this is not something we're going to spend a lot of time on. Okay. So the thing is, there are also derived units. So you might say that we have the ampere or the amp, as it's better known, but we don't have the volt or the ohm. And obviously they're very important. They're not listed here. Whereas we're going to use units that are multiples of these. So obviously a cubic meter is a meter times a meter times a meter. And we're going to look at things like a meter per second. And we're going to look at things like the Newton. And we're going to look at things like the Pascal. I don't think that's an exhaustive list of the units we're going to use in this course, but it's pretty close. Okay, so the next thing we're going to look at is you should be very familiar with these terminologies. Now, the reality is that I know that many people aren't, so let's talk about this. This is something that my school, that our data has indicated that this is something that students at our school struggle with, and it's something that we try to make a focus, and it's something that my kids have indicated to me that they have. It's something that they. I don't want to say struggle with, but I can't think of a better term, and I'm mindful of time. So let's run with that. Okay, so what we have here is, I'd like to think that most people know that a gigabyte is bigger than a megabyte, and a megabyte is bigger than a kilobyte. That's what I'd like to believe. So the idea that a kilobyte is, now unfortunately in terms of bytes and computer bytes, we might go into this later, but there's a good chance we won't. We'll say that the computer people, they're a little bit crazy, and it's not exactly 1,000, but for everything else, a kilometer is exactly 1,000 meters. A kilogram is exactly 1,000 grams. Now, we don't really use the term megagram, right? We don't just don't talk about megagrams. Instead, we have another term. We have a non-SI unit that we often use called a ton. Then I've never heard anyone talk about a gigagram or even well, I think I've heard of megatons, but really we should be talking about weight. Often is unfortunately a little bit confusing. We don't really talk about megameters. I don't think I've ever heard anything described in megameters. If you generally say that the distance from Sydney to Perth is 3,000 kilometers, you wouldn't say it was 3 megameters. But the idea is that for some units, we will definitely use mega. And very occasionally in this course, we will use giga. We use gigapascals that we'll talk about later. But just, we should be familiar with this. We should also be familiar with this notation. This notation is called scientific notation. The idea is, rather than writing a 1 with 3 zeros, we can just write 1, or we can write 10, with a little 3. And that indicates how many zeros. This 10 with a little 6, what it really means is 1 with 6 zeros. This one here is 1 with 9 zeros. It means that there is a billion, and then a million, and 1,000. Now, I like to point out that it's always a lowercase k, even though literally today I was watching a video about scone songs with my children, and they had kilometers where they had little k, big M, and I'm like, that's wrong! And, big K, little m, and I'm like, that's wrong. Anyway, the point is it should be little k, little m. Then that's important. I believe it's important. Okay, going the other way, we can make things small. So we know that, well, in this course, you'll notice that centimeter isn't here. And the reason centimeters here is because generally we like to use things in units of 1,000. So we have 1,000 millimeters make up a meter. 1 million micrometers equals a meter. Now, it's also, we could mention quickly nano and pico, but the fact is, in this course, I will almost never refer to nanometers and picometers. And to be honest, I would actually get them wrong. I have a 50-50 chance of getting them wrong if you asked me on a quiz show which one is which. Maybe I'd get there and remember that nano is smaller, but sorry, nano is bigger. I think that just makes my point. Okay, so moving on. Again, if you're not used to this, if you're not used to prefixes for numbers, then again, that's something, let me know as your teacher. If I'm your teacher, let me know. And this is something that you can really spend some time on Khan Academy or a similar thing just to really practice this and get it under your belt. We will be using these prefixes a lot, and it's important that you have a really solid understanding of them. Okay, now I've already mentioned Pythagoras' theorem and trigonometry ratios. You should be familiar with these. If you are not, you need to let me know. I will usually have a test early on just to make sure that I can identify people who have problems with trig ratios. And if you struggle with trigonometry, I will tell you that I did not really understand trigonometry till I was year 11. I mean, I probably shouldn't say that on a recording because, might be a little bit embarrassing, but I'm going to put it out there. I'm going to stop the trigonometry shaming, and I'm going to say I just always multiplied the thing by tan or sine. I never understood that sometimes you need to divide by tan or sine. I just didn't know that. So I just crossed my fingers, and I didn't understand why I got it wrong half the time. Sine and cosine rule, like I said, I don't think I've used that in the last 5 years as a teacher. I just always find other solutions, but handy I do know them, and they are handy to have up your sleeve. Okay, so the next thing we're going to talk about is scalars and vectors. So I have notes specific to this where I make my reference to, vector the character. But the idea is that everything we measure in the world can either be classified as scalars and vectors. The same way that when Elon Musk sold not a flamethrower, and if you compare that to flamethrowers, everything in the universe can be classified as either flamethrowers or not flamethrowers. Every measurement in the universe can be measured as scalars or not vectors. Just to try and make this video a little bit more interesting, when we last talked about scalars and vectors, when I went through my notes, I didn't mention some interesting fictional units. So for instance, probably the best one is the unit of the Helen, right? So the idea is that in Greek mythology, in the war against Troy, when the Greeks went to war against Troy, they went to war over a woman called Helen of Troy. Well, she was originally from Greece, but she went to Troy. Anyway, the idea is that she was so beautiful that they say that she was the face that launched 1,000 ships. So the idea, and that if each ship had 100 people in it, that you could say that 100,000 people went to war for Helen. So that you could refer to someone's attractiveness. Let's say, I don't know, I'm going to say Ryan Gosling. I think he's generally considered to be a pretty attractive guy. You might say that Ryan Gosling was a milli Helen. That means he's attractive enough that 100 people would go to war. That's a milli Helen. Or you could have micro Helens. And you might say, that guy at school, he might be 3 micro Helens. Or that girl at school might be 3 micro Helens. Anyway, in the case of Helens would be a scalar quantity because the quantity doesn't have any inherent direction. Now, if I was to drop a pen and I was to drop that pen, the direction of its travel would be towards the center of the earth. I could draw a line that shows the direction that pen has traveled. And by doing so, I've given it a direction. So, as vector tells us, a vector is a quantity that's defined by having both magnitude and direction. Oh yeah, right? So that's the important thing. Now, Copeland goes on to say it actually has 4 things, but if you're in my class, you can get away with magnitude and direction. Oh yeah, that's it, right? I'm going to move on. Okay, so the next thing I went through more recently in my mechanics notes is that there are Newton's 3 laws. Now, I went through this in, again, painful detail, but I'm going to sum up those, and I have this video that I love from the 80s that goes through it again in, cartoon glory. Anyway, I like it. And these 3 videos, they talk about Newton's 3 laws. Now, Newton's 3 laws, they don't describe everything. They start failing when we talk about really, really big things like the sun, and they start failing when we start talking about really, really small things like electrons. But for everything else, they're pretty good. They're a really, really great starting point when we're talking about physics. So what are the three laws? Well, the first law is everything wants to keep doing what they're already doing. Right? Another way you could say is things are lazy, but you really shouldn't say things are lazy. You really shouldn't even say that things want to do things. So you can't really say that things want to keep doing what they're already doing, because unless it's a living thing, well, it probably doesn't have a consciousness, and therefore it doesn't want anything. So probably a better way to write that is to say a body at rest will remain at rest, and a body in motion will remain at motion until acted on by an unbalanced external force. Right, I can live with that definition. That's a pretty good definition. But I think if you internally think of that as things want to keep doing what they're already doing, that is a really good internal understanding of what's going on. Okay, Newton's second law is often referred to as force equals mass times acceleration. The problem is there's three concepts there that may be unintuitive to everyone. So the first concept is, what's a force? Well, if you've seen Star Wars, you might have some concept of what a force is. I personally now have very mixed feelings about Star Wars. I was once a very, very big fan, and I saw the original Star Wars like literally hundreds of times. But now I kind of resent everything about Star Wars, so probably wasn't necessary for that to be on the recording, and yet I'm not going to edit it out. Okay, so a force is a push, pull, or twist. A force is an object that causes something that if it's not resisted, will cause an object to move, to push, to pull, or to twist. Now, in the SI units, right, so the units we use in the metric system, we measure forces in a unit called a Newton. And a Newton is equal roughly to the force of an apple falling under gravity. But because gravity is not the same, when I say gravity, I'm talking about Earth's gravity. The force of an apple on Earth is different to the force of an apple on the moon. So what we need to actually define a Newton more specifically as 1 kilogram moving at 1 meter per second per second. Now, what is that per second per second? That's a bit confusing. So let's go back to that. Okay, so we've defined what a force is, and we've said it's measured in newtons, and newtons is written in capital N. It has to be capital N because it was named after a living person, Newton, Isaac Newton. Ironically, when you write the word Newton, you write it in lowercase, but let's not worry about that for now. Okay, so the next thing we're going to talk about is mass. What is mass? Well, again, in my notes, I describe this in a little bit more detail, but mass is a measure of an object's inertia. What's inertia? Well, inertia is the concept that things are lazy. Things want to keep doing what they're already doing. Mass is how we measure inertia. You might say, hey, that's a really big thing. I bet you it's going to be hard to push or pull. And then you get close and you realize, it's actually styrofoam. I actually think that this will not be very hard to push or pull. The reason for that is its mass. Now, often people use the term weight, but weight and mass are not the same thing. Now, you might have said your whole life that I often say, now, this is a lie, right? So, Mr. Zeech, if you're listening to this is a lie, and I know it's a lie. But I like to say that my mass, or people might say incorrectly, what my weight is 83 kilograms. Now, I know it's not, Mr. Zeech, calm down, but for the sake of argument, the 83 is an important number that I'll come back to later. But the idea is that that's my mass, not my weight. If I went to the moon, If I went to the moon, my mass would stay the same. It would still be 83 kilograms, but my weight would be substantially less. It would be like, I don't know, 140 newtons. We're getting ahead of ourselves. Okay, the point is that the planet that you're on affects your weight, but it doesn't affect your mass. So that is measured in kilograms. Now, how we define kilograms is a bit of a crazy thing, right? Basically, it's simple enough to say that once upon a time, there was a piece of metal in Paris or near Paris, and everyone decided, they all agreed that this was going to be 1 kilogram. Effectively, it was the same as 1 liter of water, but you can't have 1 liter of water sitting around. So they took, which liter of water, So what they did is they took this cylinder of metal and they said, this is going to be 1 kilogram forever. Now, eventually we got to the idea that we said, well, okay, the big problem is that mass actually got lighter. I've mentioned in other recordings some excellent podcasts and some YouTube videos that will give you some good understanding of that. But the idea is that we have replaced that silver cylinder, and it's actually not silver, it's iridium, I think. But the point is we have replaced it. It's silver in appearance, in color. We have replaced it, and we've now, we measure everything with kilograms. A great video, if you want to watch, is a song sung to the tune of Sweet Caroline that's called Weight versus Mass. I'm sure you'll be able to find that on the internet. Okay, the next concept is acceleration. Okay, well, what is acceleration? I think most people have some idea of acceleration. Acceleration is when things are getting faster and faster. What most people don't understand is that when you drop something, that object that you're dropping is not falling at a constant rate. The moment that it leaves your hand, it's barely moving at all. But then slowly, but so fast that I shouldn't use the word slowly, progressively, it gets faster and faster and faster. Now, all objects get faster and faster and faster, unless, if you drop them, until they hit what is called their terminal velocity. Really beyond the scope of this course. I have mentioned it in other videos. I show a video of Keanu jumping out of a plane to chase someone and talking about their relative terminal velocities. But for the moment, we're just going to say that when we drop things, they fall faster and faster and faster. They accelerate. Now, how fast do they fall? Well, on Earth, when you drop things, as long as there's no wind resistance, everything falls at 9.8 meters per second every second. Their speed is going to increase by 9.8 meters per second every second. About 3 kilometers an hour. They travel 3 kilometers. Their speed increases by 3 kilometers an hour every hour. 3 kilometers an hour every second. That's how fast they speed up. So initially when you release it, it's going 0 kilometers an hour. Then it's going 3 kilometers an hour in the first second. Then roughly, I'm rounding. The second, it's now going to be traveling faster. It's now going to be going 6 kilometers an hour. The next second, it's going to be going at 9 kilometers an hour. The thing is, we don't like to use kilometers an hour because hours aren't SI units. We like to use seconds. So instead, we divide everything by 3.6 and we use meters per second squared. And I like to write it as meters / second little 2. But this is how physicists like to write it because I guess they think it's going to be less confused by other people. Okay. That's a lot to take in, and hopefully that should make sense to people because you're watching this as a summary and not as the first time you're learning this concept. At the very least, you should have watched the Eureka videos that I recommend so highly, or you've watched, or I've gone through as a teacher these notes in class. Okay, so now that we've got these concepts, let's move on to the third law. For every action, there's an equal and opposite reaction. Now, people often use this sort of metaphorically to talk about things like karma, what goes around comes around. The idea is actually more concrete. The idea is if you sit in a chair, that chair, the weight that you apply onto that chair, that force due to gravity that you apply onto that chair has to match it. If that chair can't match it, it's going to break. It's the job of engineers, or at least structural engineers, to build objects so that your weight doesn't cause it to break. That's what we're all about. So we want to make sure that we can provide objects that match, that they provide an equal and opposite reaction. If they can't provide enough reaction, the thing's going to break. This is really important. This is the job of engineers. Okay, so now we've got some definitions. We've got mass. Okay, so this definition I don't really like because I just feel as though it defines the mass as the kilogram, but it doesn't tell me what that is. So yeah, that's right. I just had someone say then that it's a measure of how much stuff the object has, which is from the song I mentioned earlier. It's a measure of how much stuff. It's not necessarily related to size, but what we're going to say is it's how difficult it is to move an object with a force, how difficult it is to push it, how difficult it is to pull it, how difficult it is to twist it. Okay, the next concept is a force, which we talked about here, is a push or pull. I think that ignores twisting, which is another way. We also have things like shearing, which is a kind of force. We have bending, but push or pull is a pretty good answer. That's the answer that if you had to define a force, I often ask students to define a force. I do that from year 9. I ask students to define a force. And often they'll say, force equals mass times acceleration. Like, great, now you've just defined something by giving me more things to look up. and it's just going to be this great big circular reference. But I do really like that answer. A force is a push or pull. That's a gold standard. I think if you look up Wikipedia or other encyclopedias, they say things similar to that. Now, even in Year 9, I like to people to be more specific. I like to say there's different kinds of forces. There's compression, there's tension, there's shear, there's bending, there's torsion. But we're not going to worry about that for the moment. That's all in our future, and some of those things aren't even in the HSC course. Okay, the next thing is gravity. Okay, gravity. Okay, well, back it up. What is a force? Okay, so Kierkegaard is or in a nutshell, they're a German YouTube video company, and they have some great educational videos. And one of them is, what is something? And it talks about forces. It says that it uses the terminology, and this is getting a little bit deeper than the course requires. But I'll just run this through quickly in our revision, and then I'll move on. The idea is that it likes to think that, imagine that the world we live in is a game. And in that game, we have pieces, we have the objects that are part of the game, and then we have the rules that tell us how those pieces should move. So in this case, the pieces, the things that we interact with, that's matter. And matter is made up of stuff, right? Protons, neutrons, electrons, that sort of good stuff. You could say that atoms are made up of stuff that's more than protons, neutrons, electrons, things like bosons and quarks. But we're not going to worry about that. What we're going to worry about instead is we're just going to say that things are made of stuff. We're going to accept that for the moment. And what we're going to say is that the rules of the game are the 4 forces. There's only 4 rules. The whole game of life is controlled by 4 forces, which I think is amazing. Only 4 rules in all of life. As best as we understand, there's only 4 rules. And the best part is, in this course, we only worry about 2 of them, right? I'll go through the 4 forces. There is gravity. There's electromagnetic force. There's the strong force and the weak force. I'll go through those last 2 first. The strong force is what holds the middle part of atoms together. Now, we only really worry about this force when we're talking about nuclear energy, when we're talking about stars or nuclear reactors or atomic weapons. Then there is the weak force. The weak force is responsible for radiation. The next force that I mentioned was electromagnetic force. This is the idea that protons have a positive charge and electrons have a negative charge, and that 2 protons don't want to be next to each other because they've both got positive charges, and electrons have negative charges, and pretty much everything else comes from that. Electricity, atoms, all of that's held together by this electromagnetic force. Pretty crazy. Then we have gravity. And gravity, ironically, is the one that we, as scientists, understand the least. This is what the people at the Large Hadron Collider underneath France and Switzerland, in a giant kilometer-long tunnel, that's what they're trying to figure out. They're trying to understand the nature of gravity, which is the thing that we know the least about. But in this course, what we'd like to think about is we often like to think about how gravity and the electromagnetic force effectively act as a fight. In the red corner, weighing in at, well, having a mass of 83 kilograms, except not really Mr. Zeech, we have, or more accurately, weighing in with a weight of 830 newtons, we have Mr. Punzett's force due to gravity, his weight. Hey! What corner did I just say? Red or blue? So I should have said blue because, I always wear the blue shirt. Anyway, in the other corner, we have the atoms that are holding Mr. Punzett together. Right? When I sit on a chair, my weight is trying to fall through the chair. My weight, my force due to gravity, is trying to force me and my atoms down into the center of the earth. But you know what? The chair says no at the moment. Maybe one day I might sit on a smaller chair and I might be a bigger Mr. Punzett. And when that day comes, one day gravity might win, right? And the best part is, in most of the time, gravity always wins. If I was doing this recording in front of a class, I often like to try and jump as high as I can just to demonstrate how gravity always wins. The only time gravity doesn't win is if you have a rocket. And if you don't have a rocket, sooner or later, gravity always wins. But the job of engineers is to try and, we are team electromagnetic force. We want to try and build things so that their atoms are going to stick together and they're going to say to gravity, no, not today. But sooner or later, gravity always wins. Okay, so that's me talking about gravity and forces. Basically, I mean, like I said, we don't really understand how gravity works. But what we know is that if you have a whole bunch of stuff, it will attract other stuff. It's a crazy thing, and we know that it's affected by an inverse square law, which means that gravity is less important when it's a long distance away than it is when it's a short distance away. But the point is, we know that stuff likes to draw in other stuff, and the biggest stuff near us is the Earth. And going a little further afield, the sun, right? The sun cannot escape the Earth. We cannot, the Earth cannot escape the sun, and we cannot escape the Earth. Now, the rate that we fall on Earth, as Alicia Keys might tell you, because she keeps on falling at 9.8 meters per second squared. But in this course, we're allowed to use 10 because, it's just easier. Okay, this is where we talk about weight versus mass. They're not the same thing. Let's all see why. We're not going to see why because that song is later. Effectively, what we can use, if you're on Earth, we can just take your mass and multiply it by 10, and then we have our weight. Doesn't always work, but it's going to work for this term. Okay, so the idea is that if we know that force equals mass times acceleration, well, gravity is the acceleration, g is the acceleration due to the mass of the Earth. So we're just replacing a with g, and then we get weight equals mass times gravity. And as I said, if we knew that a power drill had a mass of 1.5 kilograms, it would have a weight of 15 newtons. Okay, now this point here, at the time I'm recording, I haven't recently gone through simple machines with the students in this class. So that's something we need to talk about. The short version, and this one is one of the times where I'm going to be very brief in this revision. I'm just going to say there's two simple machines that we need to worry about, the inclined plane and the lever, and then as a bonus, the pulley. The pulley. Now you might say, but sir, you just passed through screws and wheels and axles. I'm going to say, yeah, but screws are really just inclined planes, and wheels and axles are really just pulleys. Really just levers. But pulleys, they're pretty amazing. Now we need to learn about things like mechanical advantage and velocity ratios, but for the moment, I'm going to skip that. Okay, brings us to materials. Okay, so to start off with, when we talk about the book, first of all, you have to understand that everything is made of atoms, right? Small things that can't be easily divided. Everything is made of atoms. There's only 100 or so of them. I mean, there's like 108 depending on who you listen to. But there's only 92 that occur naturally, maybe 93 depending on if you count plutonium. It does occur naturally, but in tiny amounts. And then there's some ones that are made in the lab. Not all the ones that are made in the lab don't count. I mean, I think some of them don't count. But like things like, I like to say Americanium, knowing that it's not pronounced that way. It's actually pronounced Americium. Americium is makes your smoke detector work. Basically, in your smoke detector, there is a thing that shoots out radiation, right? The Americium shoots out radiation, and you have a Geiger counter, basically, something that detects radiation on the other side. When your dad cooks bacon in the fry pan and it starts smoking up the whole house, well, that smoke blocks the radiation. The radiation isn't being detected by the radiation detector anymore, and that triggers a circuit that starts beeping. Pretty amazing, right? The point is, Americium is a man-made element, or a synthetic element is probably a better way of phrasing that, and it did not exist on Earth until humans created it. Or at least I can say it with some degree of confidence. What I also think is interesting, and I sometimes talk about, but I haven't talked about with these current students, is what was interesting is that sometimes you hear about like strange crimes. There was a guy who was so interested in like nuclear bombs and things that he started going around to people's houses stealing their smoke detectors so that he could get as much Americium as possible because he couldn't get his hands on uranium. It's really, really hard to get your hands on uranium. So instead, he got his hands on stacks and stacks of Americium. And when they caught him, they found that he had like a really fatal amount, or just short of critical mass of Americium in his like back shed, and his face was just covered in radiation burns. I'm too lazy to look this up now, but anyway, fun story that I sometimes tell students. Anyway, so that's elements, and then we've skipped over. I like to normally talk about compounds and say that when elements, when they mix in exact ratios, we call that a compound. There are different kinds of compounds that we'll learn about. There's covalent compounds, metallic compounds, and ionic compounds, and they order themselves in exact ratios. In table salt, there is exactly 1 sodium for every chlorine. In water, there is exactly 2 hydrogens for every oxygen. In in aluminium oxide, there is exactly 2 aluminiums for every 3 oxygens. Okay, but we'll worry about that. Before we get onto these compounds, what we'll talk about is solutions. Now, I talked about solutions in my last recording in some great detail. Effectively, when we think about solutions, what we typically think about is if I take some salt and I stir it into water, eventually the water starts separating out the salt, and it dissolves the salt into the water. Now, when I say dissolve, I'm actually using a form of the word solvent, right? And when we dissolve things, what we have is one thing absorbing the other thing. Now, typically we think about that in liquids, but in this subject, we almost never talk about liquids. What we talk instead about is solid solutions. And when we talk about solid solutions, what we're talking about is alloys. We're talking about things like brass and bronze, and the one that I said that was the most important engineering material, steel. They're all solutions. They're all solid solutions, which I think is a pretty new concept. I don't think I've ever taught a student who already was familiar with that concept. So we're going to talk about that later when we talk about interstitial and substitutional alloys. But for the moment, you just need to know that solutions are another term for alloys, I guess is probably good. Okay, mixtures. We come across many mixtures in our day-to-day life. Things like, in engineering, the main ones we like to talk about, ferrite and cementite, could be considered as, that's a tough one. But they could be considered as mixtures. I would argue that they're probably more solutions. But salt and pepper, milk, seawater, air, the air that we breathe. Trying to think of more solids. Dirt would be a good example. Okay, rice. Yeah. Okay. So I mean, when I say rice, I mean flour, meat. Okay, metals and non-metals. Again, the same way as flamethrowers and not flamethrowers. That kind of covers literally everything in the universe. But I said earlier there's 92 naturally occurring elements, that's assuming you're not including plutonium. But let's move on. Of those, 70 of them are metals. Almost all of them, well, like a big chunk are metals. Some of them are not metals. Some elements are not metals. Okay, what's the difference? That seems like a pretty arbitrary term. What is a metal? What did you decide? Well, a metal is usually a solid. Well, I don't like things that say usually, so let's say what else. They're usually, when they're solids at room temperature, well, when they are solids, usually when you cut them, they're lustrous. That means they're shiny. They can usually be malleable and ductile. Now, technically, the technical term to say malleability is the ability to be formed under compression, whereas ductility is the ability to be deformed or to be shaped or to hold a shape when being stretched under tension. But generally what we say is malleability is the ability to be hammered into a sheet. Mallus, I think, is the Latin word for hammer. And ductility is the ability to be drawn into a wire, right? Just, we'll use that. That's true of most metals. They are usually very good at conducting electricity and heat. Also, metals can form alloys, which, I mean, I don't know if all metals form alloys. I'm sure they all can, but some more. I mean, we'll learn later about powder metallurgy, is that not everything forms good alloys. Okay, on the other hand, metals are far more likely to be liquids or gases at room temperature. They can be solids. I mean, obviously things like, salt, right? Is an example that comes to mind. Sugar. Usually dull if solid, Diamond is an exception. They're generally brittle. Now, brittle in this case, we will cover these terminologies later, but the idea of brittle is, does it shatter easily? If you hit it with a hammer, is it likely to absorb that hit and have like just a dent, or is it likely to shatter? Usually thermal and electrical insulators means they don't conduct electricity well. They can be used to insulate electricity, or they're just simply are poor conductors. They can form compounds, but not alloys. Okay. A couple of exceptions. So mercury is a liquid at room temperature. Gallium is pretty close. Sodium is only lustrous for a few seconds. Sodium is very, very reactive. Diamond is an allotrope of carbon, but we don't know what an allotrope is yet, so that's probably not all that useful. You can see it's on page 16 though. Okay. Now, in this subject, we categorize all materials on Earth into flamethrower. No, we categorize all materials into metals, ceramics, compounds, or starts with a P. Polymers. What's a polymer? Plastic. Excellent. Okay, so metals. We just learnt what metals are, so we don't need to worry about metals too much. Yeah, generally we use steel is the most commonly used one. We do use the other main metals that we use are aluminium and copper-based alloys. There are some others that we're interested in, things like lead and titanium. We use tungsten carbides for things, but yeah, for the moment we're going to leave that. I think that's good enough for the moment. We've already talked enough about metals. Okay, ceramics. Well, I have gone through a recording where I went into a lot more detail about ceramics. But ceramics come in a number of varieties. Basically, when we think of ceramics, we think of things that are hard, the things that will generally crack rather than deform. If you hit them with a hammer, they don't leave marks. Instead, they just crack, or they don't leave dints. I'm going to run out of juice. Could you please get me the power? Thank you. Okay. Ceramics, okay, well the older ceramics are just rocks. When we say rocks, we don't really like that term. That's I guess we do use rocks as a term. Okay, but the idea is that we generally have three categories of rocks: igneous, sedimentary, and metamorphic, but we don't worry about that in this course. If you go on to be a geotechnical engineer, you might need to worry about that, but that is not something I would worry about now. Okay, so the next most commonly used ones are clay ceramics. So things like bricks are made out of clay ceramics. Your toilet is made out of or maybe your sink is. You take this in. Okay, but bricks are an incredibly important resource. When I did my notes, I talked about a podcast on bricks that we listened to. Yeah, bricks pretty important. I did my honours thesis on mud brick structures in their resistance to earthquakes. Okay, so the ones that we use a lot in engineering, we're interested in cement-based ceramics. The obvious one being concrete, but also just joining bricks, we use cement-based ceramics. The other one that's really important, and the one that you can point to in pretty much any room you're ever going to be in, is glass. So there's four different main kinds of glass that we use in our subject. The picture that I use for all of my notes is a picture of Ariel from Little Mermaid wearing glasses. I don't know. It's kind of a Punzit tradition at this point. There's a couple of other things that we talk about. We talk about semiconductors. We talk about insulators that are used in, say, overhead wiring and and electrical transmission lines. Theoretically, you could also talk about superconductors, but definitely not in this course. So, yeah, let's move on. Polymers. Well, I remember when I was in high school, and I remember reading a page that for some reason I wrote down, and my friends and I created a song to it. It's a terrible song, but I'm going to sing it for you here, right? The line of this book, which I can remember to this day, more than 20 years on, is polymers, dun, 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 are long chains of carbon compounds called monomers. The monomers don't have to be the same! right? I will probably remember that till I die, the day I die, or until I, lose my faculties. Okay, but polymers are a term. Okay, I'm not going to read that. Polymers, all I want to say is they're long chains of carbon compounds called monomers. The monomers don't have to be the same. We're going to get to that pretty soon. What is another way of saying that? Well, you can take some compounds, right? Like the best example that I like to use is that if you take sugar is a carbon compound. Sugar has 6 carbons, 6 oxygens, and 12 hydrogens. That's a carbon compound. We could call that a monomer. You join 2 sugars together. Well, actually, there's a couple of ways you can join 2 sugars together. You can have glucose, you can have fructose, you can have lactose. You have all these different kinds of oses. But let's start off with, if we start off with glucose is a monomer. It has 6 carbons, 6 oxygens, 12 hydrogens. You join 2 of them together, you've got a double sugar. Right, let's go with sucrose. That's the white stuff that you put in your coffee. If you have dozens of them joined together, well, now we're going to start calling those starches. Where do we see starches? Bread. Yeah, so potatoes, wheat, and rice. They're the 3 main starches that we use. Right, they're a great source of energy because they're really just sugars stuck together in long chains. But here's what's interesting. If you start taking hundreds or thousands of sugars stuck together, could you put that away? Hundreds or thousands of sugars stuck together. It's not called a starch anymore. What's it called? It starts with an F. Fiber. And we can't eat fiber. Cows can eat fiber, but we can't eat fiber. But fiber is important. Why is fiber important? Because it helps you poop. Right, so the idea is, and then fiber. Why is fiber important as an engineering material? Well, the proper term for fiber is actually cellulose, and so here we see that cellulose fibers, they're part of what we use to make timber. The stringy parts of timber. When you look at timber and you can see the grains, they form stringy components. Those stringy components are cellulose fibers. They're just made out of complicated sugars. When I say complicated, I just mean stacks and stacks and stacks of sugar. Right, so many stacks of sugar that we can't eat them, right? Okay, so what's also interesting is that the resin that holds that fiber together, which I looked up last time, I think it was called lignin, is also a polymer, but it's way more complicated than sugar. It's like a super complicated polymer. We're not going to worry about that. Okay, but most people, when they're talking about polymers, they're not talking about, starch. They're probably, or fiber. They're probably talking about something else. What are they probably talking about? Can someone give me an example? Plastic. Yeah, but what kind of plastic? I mean, plastic. So plastic is, what's interesting is that plastic in English, in English, when the average person says plastic, they mean a specific kind of material. When an engineer says plastic, they say ability to hold its shape, the opposite of elastic. Did you know that? There you go. So plastic means the ability to hold shape. The same way plasticine is plastic. Yeah, Play-Doh, it's plastic. You press it and it holds its shape. That means plastic. If it's elastic, it means it returns to its original shape. You put your finger in it and it springs out. If anyone's ever seen memory foam and things like that, where you put your finger in it and it expands back out, that would be an elastic thing. Or obviously people are familiar with rubber bands. Or steel is elastic. Do we think of steel as being elastic? No? What about a ruler? Has anyone ever taken a ruler, a metal ruler, and gone dong, dong, dong? Or a spring? Like, I don't know if you've heard me. I've tried to avoid doing it, but those people listening, I've been playing with my pen, which is spring-loaded. And that's metal that's behaving elastically. So, but could you name a plastic for me? Like, could you name a type of plastic? Polypropylene. Oh, good answer. I like polypropylene. I think if I had a favorite plastic, polypropylene would be it. Anyone who likes Tic Tacs, like the boy from Juno, they'd probably like polypropylene too, because it's the one that can have a living hinge. You can make lunch boxes that can have a hinge that's part of the lunchbox and doesn't fall off. Polypropylene is pretty cool. Polypropylene is the challenger. We'll come back to that. Okay, the one that most people I think would come to mind is they'd think of PVC. Have you ever heard of PVC? Pipes. Yeah, pipes, polyvinyl chloride pipes. So a lot of your drinking water comes through PVC pipes. It can. You can also have floor tiles made out of PVC. You can get clothing made out of PVC. What's clothing made of PVC called? No, starts with a V. Vinyl. Have you ever heard of vinyl clothing? Like jackets. I grew up in the 90s, and that was when there was this fad in fashion called industrial. So it wasn't just goths. There's still goths, right? Yeah. So instead of just being a goth, if you were a goth who wore PVC, you were industrial. Anyway, I had friends who were industrial. My brother was going out with a girl who she was really into industrial fashion. Anyway, moving along, PVC is really important. Also, this morning I was driving with my kids in the car and we were talking about records, the old records, and I think I even specified vinyl records. So that before CDs, I don't know, do you know what a CD is? Do kids still these days know what CDs are? Anyway, before CDs, we had vinyl records and they were just made out of polyvinyl chloride. All of the light switches that you see around you, they're almost certainly made out of PVC. The cables that you see around your electrical cables, they're almost certainly PVC. PVC is great. We use it for stacks of stuff. The only problem is if it catches on fire, it's poisonous because chlorine gas is no good for you. So that firefighters have to be really careful because there's PVC just everywhere.
Is that why electrical fires are like that?
Yeah, I don't know. It's a complicated question. I was asked about, is that why electrical fires like that? I'm going to say, I don't know. I'm not a firefighter. Anyway, what I'm going to move on to is, we will talk about the six, you know how sometimes you might see a triangle on your drink bottle? Yeah? What I might do is I might get us to find a drink bottle out of the recycling and we might look at them. But in a second, you can do that now. They'll bet you there's a triangle on that. Yep, okay, I'm excited. Number one? PET. Now, I'm not entirely sure. I think it's like polyethyl tetrafluoride or something like that. I don't know. I don't remember. All I know is it's PET. Number one, PET. But we're going to get there. There's 6 of them, and then there's another 7, and then there's like another 5. But we're going to get there. Don't worry. It's going to be great. It's going to be great. Okay, then I don't like... now, I'm going to say I like almost everything that Copeland writes in his book. Almost everything. I would say I agree with 95% of what he does. I don't like that he uses meters to the power of 4 rather than millimeters to the power of 4, but that's a whole nother situation. I don't like that he has biological materials here because I just don't think we need that distinction. I think we can just move straight on to composite materials. And composite materials are when we have 2 different kinds of materials together. Now, that doesn't mean that one has to be a metal and one has to be a polymer. No, it just means 2 polymers can be a composite material. Now, I mentioned earlier that timber is made of 2 polymers. We don't think of timber being made out of plastic, but they are. They're made out of 2 different polymers. Yeah, polymers of sugar. Well, partially made of sugar. Fiberglass is a composite of glass, which is a ceramic, and polymer resins. We can have plywood, which is a polymer made of polymers. Right? It's a composite of anyway, crazy when you think about it, right? Probably the most important one is reinforced concrete, which concrete is already a composite material. And this brings me to the most important thing you need to know in this subject to not embarrass me. Rule number 1 of engineering is concrete is made of sand and aggregates. Oh my God. Am I going to have to edit this? That is so embarrassing. Oh my God. Oh, fire this guy. But I'm going to keep it in. You know what? Because I want you to really pay attention here. Some of you will say, wait, Punsit made a mistake, and they're going to love it. It's going to reinforce that memory. Your neurons, they're going to shape themselves. They're going to rewire themselves, and that's going to make a more indelible mark in your memory. You're going to concrete is made of, say it again? Cement and aggregates. Beautiful. Thank you so much for that. It's almost like I planned it. Okay, but what's an aggregate? Sand and rocks. Okay, yeah, I can accept that. So the idea is that when you want to make some concrete, well, first of all, you got to get some cement, right? The Romans, they didn't have cement. They used volcanic ash, right? We're just going to accept that for the moment. Eventually, thousands of years later, someone came up with this stuff called Portland cement, right? And that's what we use today. But it's important to know that for 1,000 years, the world forgot how to make concrete. I think that's amazing. Amazing. right? The conditions that caused Rome to be the first city to hit 1 million people meant that there were lots and lots of people living in a very small space, basically because of slaves. Sorry?
They made the apartments.
That's right, they made apartments, and to make apartments you need concrete. But eventually Rome fell. Rome was no longer the capital of the empire, and eventually it just went to ruin. People couldn't afford to live in, there was no more people handing out free food. So they had to leave Rome. And eventually people said, "Oh, Dad, no one needs to worry about that concrete stuff. That's only for people who live in Rome. And no one lives in Rome anymore. And but I'll tell my son, I guess." And then that guy tells his son, and he's like, "Oh yeah, there used to be this thing called concrete. It was pretty good, but And eventually the technology just disappeared from human knowledge. And then eventually we restored it. We were able to not me, I'm not including myself in that we, but humanity was able to relearn the secrets of concrete, and concrete's pretty amazing. It's probably the most important building material. But puns, you said steel was the most important building material. The problem is concrete, I love you concrete, you're great, but concrete has problems when it bends, because concrete is only strong when it's being squashed, and it's not very good when it's being stretched. So what do we need? Well, steel comes in, and steel is great when it's being stretched and when it's being pushed. So you put some steel rods in there, you put some steel bars in there, and suddenly concrete, what we call reinforced concrete that has steel in it, as we say, it's bonza, which is an Australianism for very good. Yeah. Okay, it's bonza. And it's probably the most important engineering material, certainly after steel, the most important engineering material. Okay, moving on. Okay, so the next part here, and this is pretty important. I often, in class, I write down the word and the definition, and I make people find them. I've already said some of these definitions, but this is pretty important, right? We need to have terminologies. The same way that we need to have we need to agree on a way of measuring the world around us, we also need to agree on some terminologies. So what are the terminologies we're going to use? Yeah, and can I also get a water? Thank you. I don't really know how to pause using this recording device, so I just have to no breaks. If anyone ever plays Mortal Kombat 11, Cassie Cage, she has a move called no breaks. And I was talking about this with my students today, and I was saying, does that mean no brakes, as in she can't stop the car? Or does that mean she's like a personal trainer who's like, no brakes, we've got to keep working? Where's the water?
Why do you want water with L? Why do you want water with L's? Oh.
Because I've been talking for a long time. Future generations will listen to this recording, they're just going to love it. Okay. The sound that you're hearing right now is me eating chocolate elves.
Chocolate elves.
Yeah, I love them. They cost like 4 times the cost of Freddo Frogs, but they have the popping candy that makes it all worthwhile. Okay. I still have half an elf, so be warned. Now, here you can see there's a whole list of properties. Now, we know that things have properties, right? We know that humans have properties like height and weight. And you might say things like intelligence. If you were describing me, you might say sporting ability or lack thereof. You might say ability to play board games, which, that I'm okay at. You might say properties like handwriting. But when we're talking about materials, we want very specific terminologies that we want to use to describe things. So we might say, why do we like steel, as an example? Why is steel a good material? This is a question for the audience. It's strong. But what does it mean to be strong?
That doesn't fail.
Doesn't fail. That's a good answer. But we really want some more specifics here. Now, I literally have a definition written on the screen right now, but let's go through it. Now, before we even get to that, we're going to classify some kind of properties. Like we might say, if we're talking about a person's height and weight and their hair color, we might say that they were physical characteristics, right? Physical properties. And we might describe things like their ability to do sport or play board games or sing. We might say those as being more personality traits. Yeah, personality properties. So when we're looking at material properties, we're going to lump most of the ones we're interested as engineers, we're going to lump most of those into mechanical properties. This is how we consider how they interact with other things in an engineering context. That's the most important ones, the mechanical properties. But before we move on, we've got to say, well, what are the other ones? Well, we have a brief description, and we'll talk about those, and then we'll come back through them and discuss them in a little bit more detail in a second. And I'm now going to finish my elf. Delicious. Okay. So, what are the properties we're looking at? Now, it just occurs to me, okay, what are the other ones we're looking at? Well, we have chemical properties. This basically talks about how things react with other chemicals. We mentioned earlier that sodium is super reactive, right? If you take sodium and you drop it in water, it's almost an explosive reaction. When we're talking about things like petrol, like petroleum, gasoline, when we put that near a flame, it's super reactive. But generally, when talking about engineering properties in this HSC course, because we don't really talk about a whole lot of fluid dynamics and thermodynamics, we're typically going to focus on solid objects. The main thing that we're interested in when we talk about chemical properties is, does it rust? How does it react to oxygen? And remember how I love steel and how steel is great? Steel has one downside. What is steel's biggest downside? Rust. Steel does not play well with oxygen. When steel is exposed to oxygen, it rusts, right? It corrodes in a harmful way, in a destructive way. It's not super destructive straight away, but slowly, over time, it eventually destroys it. Okay, so that's its chemical properties. The second property is its physical properties. Now, we talked about, when we're talking about people, we're interested in things like their height and their weight and maybe their hair color. Well, when we're talking about physical properties of materials, the main thing we're really interested in is how dense is it? Right? When we say that steel is heavy or we talk about aluminium is light, what does that mean? It's like that riddle. What weighs more, a ton of feathers or a ton of bricks? Neither, because they both weigh 1 ton. I have not seen the steel is heavier than feathers video. Sounds like a great thing for me to put on my my class Facebook, but that would be great. Thank you for that. Okay. But generally, when we're talking about physical properties, the main one that we're really interested in is its density. How heavy is it relative to everything else? Right? Does it float? Would be a good example. Okay, the next one we're interested in is thermal properties, and this basically says, does it conduct electricity well? That's its main thing that we're interested in. Also, is it a solid at room temperature? That's another key factor. Electrical properties, but that sounds pretty similar. Does it conduct electricity or does it not? How does it interact with electricity? Okay, and then lastly, magnetic. I mean, those last three, I think they're all pretty self-explanatory. No need for further explanation. Okay, now that we've gone through those, let's learn about the most important group, the mechanical properties. So there are several mechanical properties that we need to learn about. We need to learn about strength, hardness, elasticity, stiffness, plasticity, malleability, ductility, fatigue, and toughness. Now, if you asked me what were the two most important ones, I would say the two most important things are probably strength and hardness, and toughness. That would probably be the third thing I would say. Basically, when we're interested in materials, if I'm going to make something, the first thing I want to know is, can it resist the loads that it's exposed to? Pretty much when we're talking about chairs, if I'm building a chair, I need to know that it's going to be strong enough to not collapse when someone sits on it. That's its strength. Is it strong enough to do that? The next property we need to worry about is hardness. Now, I'm giving general definitions, and I'm going to come back to this. Hardness is, well, I look at my chairs that I bought only a few years ago. And I look at these chairs, and I can see there's little scratches here and there. I can see where it's been worn on edges. I can see where, the little areas where it's been nicked and scuffed. And if I had bought a harder material, that wouldn't have been the problem. The problem is that if I'd had harder chairs, I probably would have scratched a lot of my other stuff. I would have scratched my watches and my phones. So you've got to choose what is the thing that you're going to have. If you're going to have two objects in contact, one of those two objects is going to get worn away. So we have to choose, as engineers, we have to choose which one is going to be worn away. If you want to have a sword, swords need to be hard, because if you want something to cut, it needs to be hard if you want to have a sharp edge. So that's what hardness is. The third one that I mentioned is toughness. Toughness is the ability for you to drop it or hit it with a hammer. So when I think of steel, well, if I had a big block of steel, if I go and hit it with a hammer, it's probably going to be okay. Yeah?
Pretty tough.
It's pretty tough. Whereas on the other hand, if I have a sheet of glass, depending on how thick the glass is, but let's, for the sake of argument, if I have a sheet of glass and I hit it with a hammer, it's probably going to shatter. Yeah. Even if you think about, if I had a similar amount of, for its strength, if I had a sheet of steel, right, not a big chunk of steel, but if I had a sheet of steel, if I hit it with a hammer, it probably wouldn't shatter. Maybe it would break. Maybe its strength would be low enough that it would break, it would fail. But even if it did, what would probably happen is it would bend. It would bend and it would leave a warped. It would still be broken. Don't get me wrong. It would still be broken, but it wouldn't shatter. And so we talk about that as toughness. Now we also have terms that are the opposite. So what's the opposite of strength? Weakness. The thing is, we never say weakness. We just say something has a low strength. Ironic, I know. What's the opposite of hard? Soft. Soft. I'm very happy with that. What's the opposite of tough?
Soft.
No. I've said it earlier. It starts with a B. Brittle. Now, something that is very closely related to tough. Remember we talked about the sheet of steel. If I hit it with a hammer, if it doesn't break, yeah, it's going to be malleable. Yeah? Because I'm going to actually deform that sheet of steel. If I go to my car and I hit it with a hammer, right, it's going to deform. Now, sometimes that's a good thing. Panel beaters, well, what do? They beat the panels of your car to shape it. Yeah, they beat the things into shape. Blacksmiths, when you think about them making a sword, they're hitting it with a hammer. They beat it into shape with malleability. Also, if we want to make wire, well, we don't want wire to be all sloppy and moving aroundy, right? So we want to have that hold its shape. But that's not malleable, that's ductility. Now, because of the way that we do our testing, we tend to use the term ductility way more than we use malleability. That's just because of the way that the scientists who do material testing tend to work, right? So we tend to use ductility, even though it's probably less common in practice. But we're going to learn about these rules. Let's go through it. Okay. Strength. Now it says here the ability to withstand loads. Now Copeland, I know I said only just a second ago that I didn't like something you wrote, and I'm going to say this is the second thing. If you're listening to this, well, first of all, thanks for writing a really good textbook. But second of all, and I mean, I've met Copeland, he's a great dude. Yeah, he does. He's the supervisor of marking. So when I did HSC marking, I spoke to him very briefly a couple of times, and seems like a really nice guy. But what I will say is it really should say the ability to withstand applied stress. I should also point out, Copeland, if you are listening to this, that it's really, really, really hard to write a textbook, and I appreciate that, even though I disagree with it, you probably had a really good reason for writing what you wrote, so we're good. Okay. I don't like the idea of saying the ability to withstand load. It's fine because at this point, right, this is probably why Copeland wrote it, is because we haven't learned about stress yet, and stress is complicated, and we haven't got to stress, so you've got to start somewhere, right? But my students who are listening to this, they will probably have already gone through my notes, and at my notes, we've learned about the Pascal, right? Pascal, like the character entangled, and we know that strength and stress are both measured in the same unit, and we know that stress is in fact the ability to withstand strength is the ability to withstand stress. What that means is, you might say, oh, I was able to, okay, I won't do the voice. I'll say, you might have two chains, and you say, well, this chain here on the left, it held a load of 1,000 newtons, and this chain here, it held a load of 100 newtons. Which one's better? And you say, well, they're both made out of steel, they're both made out of the same material. The difference is that, what would probably be the difference in that chain that held 1,000 newtons? The one that held it 10 times as much. What do you think was probably the difference in that chain?
How big it was.
It was probably 10 times the area. And we know that load over area is really important. Now, nevertheless, I can understand why Copeland wrote what he has, and you've got to start somewhere with your textbook, and you're never going to please everyone. So if you wrote an exam Strength is the ability to withstand applied loads. I'm going to give you that too, right? That's a sufficient answer for my exams. Personally, I'd rather you say strength is the ability to withstand stress, but I understand why you and Copeland write what you write. Okay, hardness. Hardness is the ability to resist scratching. That is the example. I mean, if I ask students, sometimes in an exam, I'll say, name one material property and describe it. If I do, 90% of students will say hardness is the ability to withstand scratching. I don't know why, but they just love it. They just can't get enough of it. Now, in our notes previously, we learned about the Morse hardness scale. I don't even know the name of the hardness scale. Why? Because it's not relevant, right? You might have a science teacher who's talked about the hardness scale. You might have had a geography teacher who talked about the hardness scale. Engineers, we don't use that hardness scale. We use the Vickers hardness scale, the Rockwell hardness scale. Yeah, that's what we're interested in. We're interested in nice empirical...
Is that the one like the diamonds?
Diamonds beat number 10? Yeah, that's the one. Yep.
Oh, we use the same one sometimes.
Yeah. So, well, no, this one here, we don't... Copeland, what you doing? You're writing the Morse... We in this subject do not use that scale, right? They're only using it here as a reference point. We're going to use Vickers. We're going to use Rockwell, right? We're going to learn all about that. I even have a story about how when I tried to contact Sam Rockwell on the internet and he didn't answer my question and how I was very sad. But he was in one of my favorite movies, the Ninja Turtle movie. Have you guys heard that story? Oh, it's a great story. You're going to love it. So this is why Sam Rockwell represents... do you know what movie he was in? Everyone's favorite movie, Moon. I know, can you see how it's all just coming up Sam Rockwell? Anyway, we'll learn about that later. So Sam Rockwell is the picture I use for my hardness testing. If I was smarter, I would link to that right now. But, I'm going to try and stick to one browser because, I don't want to make my life difficult. Okay, elasticity is the ability to return to its original shape. We've already talked about the difference between rubber and metal and steel, like how steel can behave elastically. Whereas on the other hand, things like salt do not behave elastically. If you have a big salt crystal and you hit it with a hammer, it will not spring back. It will deform. It will shatter. It won't deform. It will just shatter. Stiffness. Okay, stiffness is a great one. Not many people have a good medical... We might have other... We might have other definitions that we use in our day-to-day life for stiffness. But in this subject, stiffness is the ability of a material to resist elastic deformation under load. This is a fairly complicated one. I won't probably ask Year 11 students this until we've learned about stress over strain graphs. But effectively, it's a measure of elasticity. We're going to worry about this one later. I'm going to say this one here. You can read the definition. You can write it down in your books, which is probably what you should all be doing at this point. If you don't already have a textbook for this subject, you need to get one. But we're going to cover that in way more detail over later. Okay, plasticity is the ability to to hold a permanent shape. Now, there's two kinds of plasticity. What are they? They're literally written underneath it. Malleability and ductility. Can it be deformed? Is it plastic in compression? Is it plastic in tension? Malleability and ductility. I think I mixed those up, so they're not relative. Malleability is the ability to be rolled into thin sheets or hammered. Effectively, the ability to be deformed under compression. Ductility is the ability to be deformed under tension, to be drawn into a wire, I think is the definition, is the literal English definition. Okay, fatigue. Fatigue is a great concept. Okay, so the idea is that some objects, they can be fine under a load once. You can load up that 1,000 newtons onto that chain, it'll be fine. And you can load that load up, that 1,000 newtons up to that chain 10 times, 100 times. But when you do it 10 million times, suddenly it breaks for no good reason. Where do you think this might be a problem? Where do you think something might be subjected to repeated cyclic loading? Ooh, washing machines is a great answer. And heavy machinery can really fail under fatigue. That is a great answer. But something we cover in this course is aeroplanes. And aeroplanes, you don't think about it, but when you think about the wind, it's increasing and decreasing by tiny amounts all the time. So that plane, you don't think of the wings flapping, But at a microscopic level, those wings, and not even at a microscopic level, actually at quite a substantial level. When I say substantial, I mean like, in millimeters, not micrometers. But those wings are moving up and down many times a second. I don't want to say how many times a second, but many times a second they're moving up and down. They're vibrating, and that causes them to fatigue because these planes, they're up in the air for decades. So we have to make sure that they don't fail under fatigue. Okay, the last one is notch toughness. So we've talked about toughness. Notch toughness is a measure of toughness. So it's the ability to absorb energy without failure. So the idea that if I hit something with a hammer, will it shatter? Yeah. Okay. Chemical properties. Right. Who's that? MCR. Yeah. Anyway. Basically, we're interested in chemical properties. I talked about rust and I talked about corrosion, but we also have to worry about things like ultraviolet effects. So some plastics, they will break down when you put them in front of the sun. Yeah, they'll change under the sunlight. Yep, that's the one. Okay, when we're talking about physical properties, we're talking about here about density, which is how much things weigh per cubic meter. And then we also have to worry about things like porosity and moisture content, not things I would worry too much about. Okay, then we have thermal properties and electrical properties and magnetic properties, which I've already discussed. Okay, the next thing we have to look at here is atomic structure. Now, I'm going to be going through this a little bit faster because I just got a phone call and I don't want to have this go on forever. But when we said before that everything is made of atoms, well, we need a little bit more detail. So for a long time, people didn't really know what was going on inside those atoms. We didn't know what was happening. But eventually people like Rutherford came along, and so originally there was people like Thomson. He had an idea of the plum pudding model. You learnt about this at school, right? That Thomson, he knew there was positive and he knew there were negative, but he didn't really have any good idea about what was going on. And then I'm pretty sure it was Rutherford with the gold foil experiment. Does that sound right? Yeah. So what he did is he shot electrons, or maybe he shot alpha particles. I think he shot alpha particles at pieces of gold. I don't know why it was gold, but I think he shot at gold. And he found that there was obviously one part of the element that was more charged than the other. So he figured out that there must be a strong charge at the center of every element. And we just call that strong charge at the center a proton. Now, some people, mostly electrical engineers, they wish that they'd said it was the other way around, but this is what we got. All right, so we say that there are positive protons and electrons that go around the outside. Now, remember we said about how positive things, like charges repel? You know how they say opposites attract? You've heard that, like, in movies, romantic comedies, they talk about opposites attracting, right? Yeah, the poles of the magnet. So you have the north and the south pole, they attract each other, whereas you put two north poles of a magnet together, they push away. Exactly the same concept. So what that means is, in the center of every atom, you have a whole bunch of positive charges, and they're right next to each other. How do you do it? Crazy, right? Your whole life, how many times have you heard about protons being in the center of the atom, and then how do they stick together? Why don't they repel? Well, part of the answer is neutrons. Neutrons, these things with no charge, they kind of provide some space between the protons so that they can get along. And then, do you remember we talked about there's 4 forces? There's 4 rules to the universe. Strong force, weak force, electromagnetism, and gravity, right? The strong force is what holds the protons together. Eventually, the strong force, nucleus of atoms gets so big that they start to radioactively decay, and we call that the weak force. Weak force, strong force, way too complicated for me. I am not a nuclear scientist. We used to have one who lived underneath us, but I used to see him in the elevator occasionally and talk to him about things. Anyway, not many in Australia, mind you, because we only have the one nuclear reactor near where the Scouts is. Okay, so effectively we talked about this. Protons and neutrons, they're pretty much the same size. A neutron is less than 1% smaller, but they're pretty much the same size. Electrons are tiny, like I think at this scale, an electron would actually be like smaller than the ink that it would take to draw a dot on an eye at this scale, right? Electrons tiny. Like I think that sometimes science teachers talk about like if the nucleus of the atom was this building, the electrons would be smaller than a ball. Anyway, I don't know. Not something I worry about. Not something you need to worry about. I don't want to give you make you think that that's more likely to be a thing you need to worry about. Okay, solids, liquid, and gases. Well, as many of you will no doubt be aware that all matter can be pretty much just, well, not all matter. There's plasmas, but we don't worry about plasmas in this subject. Don't worry about plasmas. Not going to be in this course. Plasmas, yeah, well, okay. Tomato, tomato. Okay. Solids are matter that pretty much have stuck together, right? Solids can hold a shape. Liquids fill the base of the container. They can't hold the shape exactly, but they will take the shape of the container. There's a famous Bruce Lee line about you pour water in the cup, it becomes the cup. You pour water into a bowl, it becomes the bowl. Be like water, my friend. That's the line. There's a song, there's various songs that you use that quote. It's a pretty cool line. Whereas gases, on the other hand, they don't just become the container. They don't just become the cup. They don't just become the glass. Become the bowl. They fill the whole object. The gas fills the room. And here's what's even better, right? We call both liquids and gases fluids, right? So when we do fluid dynamics, what I think is really great is there's a... obviously, my daughter, she did this speech about, is the glass half full or half empty? And I said to her, well, no, the glass is neither full nor empty. It's half filled with water and half filled with air. Yeah, unless the glass is in a vacuum, in which case that's a very interesting glass. If you've managed to get a glass that's half filled with a vacuum, so and a great way of thinking about this is if you take a glass of water and then you take some oil and you pour that into the glass, what you'll see is you'll now have three fluids filling that container. So the water will eventually stir through, and then eventually the oil will form on the top, and the oil will form a layer above the water. And the reason for that is when we learned about density just a minute ago, the oil has a lower density than water. So the water goes on the bottom, oil goes in the middle, and then the gas goes on top. The air fills the remainder of the container. So if we think of it in that way, I think it's a great way of thinking about solids, liquids, and gases. Now, I mentioned right at the start of this recording about Kelvin and how no one needs to worry about that. Basically, the very short version is that when scientists started measuring the amount of things, liquids have more energy than gases. And what we found is that we could measure for any object. If we picked an object like, I don't know, gold, right? A pure gold. And we measured how busy it was, how much energy it had, how much it moved around at every temperature, you could draw a line. You could say at this amount of energy it moved this much, it vibrated this much. And as a matter of fact, all solids are even moving a little bit. They're all vibrating just a little bit, right? But as we cool them, they vibrate less and less and less. Now, we could never get them to a temperature where they stopped vibrating. But what we then found is if we took another metal, let's say silver, right? Pure silver or pure silicon, something like that, and we measured that same line, we found that everything, not just all metals, water as well, they all met on this same location. They all predicted that the only temperature where it would stop moving completely would be minus 273 degrees Celsius. And the idea is that if I said to you that the temperature today was 40 degrees and the temperature yesterday was 20 degrees, I'd say, well, already that was a very big range in temperature. But I'd say, how much hotter was it when it was 40 degrees compared to when it was 20 degrees? How much hotter was it? Okay, but as a factor, would you say it was 10% hotter, 50% hotter, 200, twice as hot? Would you say?
A bit less than twice.
Okay, so most people would say it was twice as hot. But then if I said to you, well, I'm actually American and I don't talk about 40 degrees. Instead, I say today it was 100 degrees and yesterday it was 60 degrees. Well, now you wouldn't say it was twice as hot, would you? We'd say it was only 30% hotter, 40% hotter, right? 50% hotter. Yeah, do you see that there's a difference? And that's because our temperature doesn't start at actual zero. Everything else we measure from actual zero. Whereas temperature, we just pick from an arbitrary point. And we pick different points. So there is a true starting point, and that is 0 degrees Celsius, minus 270 degrees Celsius, or better referred to as 0 Kelvin. Now, that's about as much as I'm ever going to talk about Kelvin, though I might include it in a Year 9 test, so watch out if you're in Year 9 and you're somehow listening to this recording. Okay, bonding. Okay, so the idea is that solids, they hold together somehow. There's some way that these things, these atoms, this stuff, right? We're really worried about compounds, how these things start to stick together. Now, if we're talking about pure substances, elements, well, they could just be holding together, right? I'm trying to think of examples like, argon gas, for instance. But everything else, all compounds, they form together in one of three different kinds of bonds. Now, theoretically, the syllabus doesn't say in exacting details, and recently when they were asking for suggestions for the new syllabus, one of the comments that one of the people I did marking with mentioned was that should we mention things like London forces or Van der Waals forces? And I wouldn't worry. I personally don't think we should be teaching those. Instead, we're going to talk about three different kinds of bonds. What are the three different kinds of bonds? Covalent is one of the bonds. Go. Ionic is one of the kinds of bonds. The last kind of bond starts with an M.
Magnetic.
Close. It's the dads at the barbecue. Metallic. Excellent. Okay. So, now I've gone through this in a lot of detail in my other notes. But what we're going to say is that salt, right, table salt, it forms sodium and chloride, and it forms together in a big pattern. Like imagine when you go to the shops and you see all the apples laid out on those boxes.
Yeah.
But imagine if every second apple was a different color.
Yeah.
That's kind of what we can think of with an ionic bond. We have one metal, one non-metal. Now, it doesn't have to be a 1-to-1 ratio. Sometimes it could be 2 to every 1, right? Or it could be 2 to every 3 in the case of like alumina that we saw earlier. But that's when we're talking about ionic bonds. What happens is, if we look at, can you see we have these, this is a lithium ion. A lithium ion has 3 electrons. Now, I'm going to tell you that most things want to lose that outside layer. Now, can you see how lithium, it has 1 too many electrons? And fluorine has 1 too few. It's like lithium, they want to play a 2-player game, and fluorine over here, they want to play an 8-player game. And they're like, hey, you, why don't you come and join us? Now lithium's happy because they've got exactly the number of players they want, and fluorine's happy because they've got exactly the number of players they want. But you know what? Now that lithium has got rid of this downer of an electron, right? Electrons, they're a bit negative, right? They're a bit downer, they're a bit sad sacks. Suddenly, lithium feeling a bit happier. Whereas over at this fluorine table, well, they've now got 1 more electron than they have protons, right? They have an extra electron compared to the number of protons. And suddenly, fluorine, a bit negative charge. Do you remember what we call these things when they're no longer elements now? When they're no longer pure elements when they've got an extra or one extra electron or 1 fewer electron. It's a 3-letter word. What's that word? An ion. Now, not to be confused with iron, right? The metal. Ion, I-O-N. I like to talk about how twin ion engine is where TIE Fighter comes from. Okay. Now, the same way that happens for metals and non-metals, if we just have 2 non-metals joining up, well, how does that work? Well, we might have things like hydrogens, 2 hydrogens. What they do is they say, hey, I have 1 player and I'm looking for a second player, and you have 1 player. If we join up, we can both share each other's electron, and we're now happy. They now have 2 players. They have enough to play their game of chess or Magic the Gathering, because, if they're nerds like me. Big fan. Anyone listening to this who wants a game of Magic the Gathering, let me know, and I will see what we can do. Okay, on the other hand, here what we have is we have these hydrogens. Each hydrogen has one electron, and they want to play an 8-player game. Now, carbon's like, okay, I've got 4 people, right? They're ready. They show up to the game table with 4 people ready to go, and then 4 hydrogens come along, each bringing one electron, and now everyone's happy. Now, how do you know if they're happy? Well, generally the rule is they want to have 8. Some are weirdos, like lithium. Lithium wants to only have 2. but pretty much they want to have 2 or they want to have 8, right? And we don't even really talk too much about the ones that want 2. Now that's a really gross simplification of pretty much year 10 chemistry, but for now that should be good enough for us. Now I'm going to talk about what I think is the most exciting one, metallic bonds. Okay, so there's an analogy. So I talk about how, so first of all I'll give you a definition. This is a definition that I remember learning when I did the HSC and it stuck with me. Metallic bonds consists of a lattice of positively charged metallic ions surrounded by a cloud or sea of electrons. Right? That's a pretty good definition that you can use. Okay. The idea is that metals, like lithium, they all have more electrons than they need. They all have more electrons than they need. They're called positive valence electrons, right? They all have more electrons than they need. And what they do is when they lose that electron, now they're positively charged. They're now a positive ion. So what these, the analogy that my mum, who's a chemistry teacher, taught me, she said, imagine you have a bunch of dads. Now I'm a dad, and I sometimes get resentful about people who, talk about dads as being, crap or whatever, like, Jerry and Rick and Morty. But in this particular case, I'm going to run with it because I think it's a helpful story. You have a bunch of dads, and they go to a barbecue. Now they all take along a kid, and they all leave with a kid, and 9 times out of 10 they leave with a kid that they started with. But when they're at the barbecue, no dad is particularly watching their kid. They're just like, oh yeah, all the dads, all the kids, if anything happens, someone will deal with it. So you have these ions that they've all shown up with one kid, or however many electrons they showed up with. And those electrons, they just buzz around. It's like, oh yeah, I've got electrons, not necessarily my electron. They're not that attached to them. They all leave with the same number of electrons. And what that means is because you've got all these electrons floating around, there's a lot of electrons that can carry heat, or there's a lot of electrons that can carry electrical charge. And that's why metals are typically what we use to conduct electricity. Now, it's worth mentioning things like water. Water is a covalent bond. Water cannot conduct electricity. But when you dissolve salt, an ionic bond, into water, suddenly those sodium ions and those chlorine ions, they can carry charge and they can conduct electricity. Okay. Now, intermolecular forces, right? These are the van der Waals that I mentioned earlier, also called London forces. Basically, they're just how covalent bonds turn. Obviously, there's more than one methane. There's more than one oxygen. There's more than one H2O molecule. So how do all these individual H2O molecules that are bouncing off each other, how do they hold together? What stops them just from flying away everywhere? Well, they're held together by these very weak forces called London or van der Waals forces. I think they were originally called van der Waals forces, and then in the war, no one liked to use this, I think it was a German dude, so they didn't like using a German name. So instead they started calling them London forces, and I guess that's why Copeland has chosen probably the more historically correct name. Okay. The van der Waals force is 1% as strong as the covalent force. So that's it. That's all we need to know. Okay. Now, what's interesting is that when we have all these solids, pretty much most solids, not all solids, but most solids, they form crystals. Right? Obviously, salts form crystals. We talked about that, right? They form a lattice, right? Remember, like the apples lined up on in the supermarket's shelf. They form in these regular patterns that we call a lattice or a crystal, right? So, if you've got a friend named Crystal because they're all into like New Age auras and stuff, they're probably very surprised to think that everything pretty much lines up in a crystal. Okay, so metals line up in crystals, and ceramics mostly line up in crystals, but polymers, they don't always line up in crystals. And there's one ceramic that doesn't really line up in crystals. What's a ceramic that doesn't line up in crystals? Glass. Glass does not line up in crystals. It's an amorphous solid, which means it's still a solid, it just doesn't line up in crystals. That's it, it's just that simple. Now, what's also interesting is, first of all, what are the shapes of these crystals? Well, there are different ways that we can stack apples. We can stack, and now I don't really care too much about this. When you get to uni, you might have to worry about this. You need to learn about like the units, the unit cube and all this sort of stuff. For the moment though, we're just going to learn that there's the BCC and the FCC that won't let M and M be. and let you see. Anyway, and then there's the hexagonal close packed. Now, I will tell you that there is also one that is not mentioned here, and that is BCT, and that's a great, exciting one that we have to worry about later. Body-centered tetragonal. But that is for future you to worry about. For the moment, and for future me, I guess, so to worry about. What we got to know is that we can stack apples with one apple in the center of every layer, or we can stack apples in alternating layers, where each layer sort of stacks on top of each other, but they're at 45 degrees, right? And what we call, so this one here is a body-centered cubic, this one is a face-centered cubic, BCC, FCC, and then titanium, it follows a hexagonal pattern. Don't need to worry too much about that. I will never ask you about hexagonal close packs, but you should probably know it's exist. Okay, so the next thing we need to know is, so glass, for instance, is non-crystalline, and a lot of plastics, a lot of polymers, like I'm pretty sure PVC and acrylic, I think they're non-crystalline, and then some of them are semi-crystalline. You won't need to worry about that. If I ever ask you to name a non-crystalline solid, you'll just say glass. Yeah, and I'll be happy with that, and you'll be happy with that, and everyone will get some good marks. Okay. Now, we haven't covered this in our notes yet, so I'm going to be very brief because I don't want to go through, I'd rather go through my notes. First of all, when we talk about metals, there's ferrous metals and non-ferrous metals. The same way that there's flamethrowers and non-flamethrowers. All metals can be described as iron or not iron. Yeah, that's just how much we love iron. Did I mention I love iron? Right? There's a vicious rumor out there that I love trains, but no, what I love is iron, right? I think iron's pretty cool. Ironically, Tony Stark's suit, not made out of iron, but anyway, I feel as though it's a bit of false advertising. It's probably the thing I dislike most about Iron Man. Anyway, when we talk about iron, well, okay, what is the iron that matters? Well, the main one we care about is mild steel. Mild steel, right? If you took all of the mild steel, well, okay, it's got iron, mostly iron, because it's a ferrous metal, ferrium being the Latin word for iron, and it's mostly made of iron, and in French it's fer, like the chemin de fer is the road of iron, the railroad. It's mostly made out of iron, but it has a tiny amount of carbon. Do you know how much carbon it has? Less than 1%. How much less? 1/3 of a percent. If you took a percent and then divided it into a third, that's how much percent. Or another way of saying that is 0.3% carbon. Now, later I will talk about the third most important thing you need to know on this subject, which is that mild steel has 0.3% carbon and has a strength of over 300 megapascals. But we're not there yet, so we're going to let that one go for the moment. Okay, so there are some other things we need to know about. Pure iron or wrought iron. It's, wrought iron and pure iron are pretty similar. And then later we get up to stuff like cast iron, which is way higher carbon content. And I haven't talked about this with you guys yet, but there's also this stuff called pig iron. Have I ever played you the pig iron song? Yes. Okay, pig iron, 6% carbon. Now, I will only tell this story once on recording, hopefully, where I'll talk about how a famous prime minister, the prime minister during he was the prime minister before and after World War II, was this guy called Robert Menzies. And he said Australia has too much pig iron, had too much iron with a high carbon content, and it was no good. We didn't want it, right? It was crap, so we want to get rid of it. I probably shouldn't say crap on a recording, but yet I have. I've just said it twice. Anyway, so he said, you know what? That new up-and-coming country, Japan, they want to pay. They don't have any iron, right? They have to make their samurai swords out of like iron sand. That is terrible stuff. That's why you got to fold it 200 times, yeah, just to try and get anything that's close to being reasonable. 200 times you have to fold it. Ridiculous. Anyway, so they wanted some iron, and so they said to Australia, hey Australia, can we buy your iron? And it's like, well, we're not going to sell you good stuff. We'll sell you some pig iron, right? It's got 6% carbon. It's terrible. And then Japan, they used that iron and they turned it into submarines that they used and missiles to bomb Darwin and to attack Sydney Harbour. So yeah, did not work out well for Robert Menzies, and so that's why they called him Pig Iron Bob. Yeah. Now, I mean, he died, I think, before I was born. He certainly was prime minister like decades before I was born, and yet I know this story, right? My grandparents talk about Pig Iron Bob. Okay, so the whole point is here to say that carbon content can vary really wildly. steel stops getting stronger at about less than 1%. The reason why we like cast iron is because at about 3 or 4%, I think about 4% is where it casts the most easily, right? At 4%, it's where it casts at the lowest temperature. Like you need to heat it up less. And like obviously if you have to build really big fires, a lower temperature could be good. Anyway, and then we have stainless steel. What's the big advantage of stainless steel? Doesn't rust as much. It still rusts a little bit. Now, I don't talk about stainless steel very much. It does not get tested very much in the HSC, but I do have some notes that I'm pretty proud of that I put on Facebook, on YouTube that you can watch, and that's where I use as my primary notes. So stainless steel contains at least 10% chromium or nickel, and it can also contain nickel. That's the other thing that helps to prevent corrosion.